Lesson 43, area under a curve as an infinite summation, okay? So we're using an integral, or not an integral, we haven't gotten there yet. We're using sums to find the area under a curve, right? We're taking the curve and we're dividing it into little boxes, right? Or because we can find the area of rectangles. We're seeing though that we get extra, right? So if you have a large number of boxes or of rectangles, you have less underlap or less overlap, right? So if you look at your book, these pictures, right, at the very top of lesson 43. Okay, so like this curve, it's a line, but we only use 2 rectangles, so we've got a lot of missing area here. Okay, but as we used 3 rectangles, we got a little bit less area. If we use, how many is that one? 6 rectangles, right? Then we've got even less area that's missing. Okay, so what it's saying is that's our error. Okay, our error is what's missing, or if we use the other side rectangles, then that area would be extra. Okay, so as the number of subintervals increases, right? So in the book, we went from 2 subintervals to 3 subintervals to 6 subintervals. The area or the error, the mistake, the under, what we're missing, okay, decreased. So to write a general expression for the lower and upper sum estimate, right? That's where we had lower was when you were missing some, and upper was when you were having extra. On a subinterval of A to B, we're going to partition the interval into n non-overlapping subintervals with equal width. Okay, we've been doing that. That's not different. Okay, so the area between A and B, right? You're going to take the width of your rectangles, and it's going to be delta x, is the difference in your subinterval or of your interval divided by how many you want, right? So if you want it into 4 subintervals, you're dividing by 4, okay? Because this is the length you're looking at between A and B. So that's the same, okay? A lower sum is found by computing using the lower rectangles, meaning they're inscribed under the curve completely, while the upper sum is using circumscribed rectangles. So it's going to overlap, okay, because it's an upper. And we're finding that the area is going to be between that lower and that upper interval, or that upper and lower area, okay? It's somewhere in between that. So we don't know where that minimum and that maximum are attained in your intervals. So we're going to have a least value, and we're going to say that the small, given f of x is your curve, the least value of f of x is going to be represented by f of x L1. Okay, it's the least value of the first subinterval. Okay, so then the area of that first rectangle well, we know the area of a rectangle is length times width. So the width of your rectangle is always delta x, okay? And then you found the height was the value of the function evaluated at the x where your subinterval is. So the area of that first rectangle then is this least value of your function times the width. Okay, so then looking at the flip side of that, when you're looking at the minimum value, okay, we get f of L2, okay, for the second subinterval. So then the area of that second rectangle is this times its width, okay? So this is a lower sum of your second. This is a lower sum of your first, okay? Lower is you're keeping it under, okay? So then we can generalize the lower sum by saying that the lower sum, so S sub L, is going to be all of these rectangles, okay, added together. So the lower interval of the first plus the second plus the third, okay, and this pattern continues until you have that final subinterval. Okay, if we notice, they all have a delta x because that's the width of all the bars. Okay, and then we can use summation notation. So the lower sum is going to be delta x because that's common to all of them, so you can factor it out, times the sum, that's what that weird looking e is, from I equals 1, because that's your first subinterval, up to n, where n is however many subintervals you have, of the function evaluated at the lower interval. Okay? It's kind of a summary of what we've done, right? This is the lower, and then we'll look at the upper. Okay? We'll use G. Okay? So that's the lower sum. Then, for the upper sum, we're going to say that f of x g1 is the greatest subinterval, okay? And g2 would be for the second, g3 would be for the third. So if we're looking at a general expression for the upper interval, okay, it's the sum of all the area of the rectangles. We know that they all have a width of delta x. And then, so we factor that out. Then it's just the sum of the functions evaluated at the greatest value for the subinterval, okay? So we can say that in summation notation, it's delta x times the sum from the first interval to the last of the function evaluated at the highest or the greatest value for the subintervals. Okay, again, this is kind of review. The lower and the upper sums we've already done. Okay, so then the actual area under a curve is somewhere between the lower and the upper sums. Okay, so our actual area is somewhere between the lower and the upper. And we write them using summation notation. Okay, so then we can continue the definition of the area on an interval between the curve and the x-axis as the number approached by both the lower and the upper as you get more and more rectangles. So as your subintervals get greater, these two values are going to be closer together. Okay, because again, if you look back at the book, that error is getting less. So as you get more and more rectangles under the curve, these two values are getting closer and closer together. So then we can define the area as a limit as you get an infinite number of rectangles or subintervals of delta x times the sum of the lower, and that's also going to equal the limit as you get more and more rectangles of the upper sum. So of the greatest. And these are eventually going to become equal as you get more and more rectangles. Okay, so the lower and the upper will become closer together, getting us closer to the actual value of the area under the curve. Okay, so when we talked about limits, we saw that sometimes a limit does not exist, right? But for the purpose of this text and this section, we're assuming that they both exist and they are both in fact equal, okay? It's a really large assumption to assume that they exist and they're equal, but it's not a false one, okay? So the proof is a little bit beyond where we're at, and purpose of how much time we have, plus the fact that I'm not seeing you guys right now, it's beyond. It's just something we're going to assume to be true, okay? Not really a great habit to get into, but just let's say it exists, okay? All right. So hopefully that's something you guys kind of saw when you're taking these sums, is that the more rectangles you got, the closer the two sums got to each other, which should be true. Okay. So looking at that definition of the area, you see that it doesn't really make a reference to a graph or to an area in a usual sense, okay? It just, the area contains a limit of sums of a product. Doesn't mention rectangles. We've defined it to be a limit of either two sums, and it has absolutely nothing to do with area as we normally think of it, okay? We used a graph to get started, but the definition of area stands alone without a graph. All right. So then the question asks, right, is it actually possible to find this upper sum or a lower sum, right, as n approaches infinity? Okay, because when you look at it, we said that delta x is b minus a over n. So if n gets big, right, this approaches 0, really, when you look at it as a limit, right? Because a number divided by a big number gets closer to 0. So we have to keep that in mind when we start actually looking at this idea of finding this upper and lower sum, okay? So we're going to look at an example, okay? It uses a continuous function that's constantly increasing, and it's not negative on the interval, okay? It will also be valid for continuous functions that are not always increasing, but it's kind of looked at later on. So when we're on a negative interval, we are going to get the development of a definite integral, and not there yet, okay? In fact, I don't know if we get there, which is kind of a bummer. But anyway, okay, so we want to find the exact area under a curve. When you're finding the exact area, you're going to use a limit, okay? So the exact area under the curve y equals x squared on the interval 0, 2. Okay, so start by, what does this look like? So we're going to graph this, okay? X squared is just this is going to be part of a parabola. So when x is 0, y is 0. When x is 1, y is 1. And when x is 2, y is 4. You guys should know how to graph y equals x squared. Okay, it looks like this, and we're looking at this interval. So this is the area we want, is under that curve, okay? So we're looking at drawing rectangles, right? So we're going to get closer and closer to an infinite number of rectangles. So rectangle, okay, we're looking at getting smaller and smaller, so an infinite number of these. So it tells us that the area is going to equal the limit as x approaches infinity. I changed the variable, it still means the same thing. Okay. Should be n, should not change it. As n approaches infinity of delta x times the sum of I equals 1 to n of the function at the lower limit or the lower value of the function in the subinterval. Okay? So this is what we're looking at, because it doesn't matter if we use the lower or the upper because the limits are going to be the same. Okay? So we know the width of each rectangle is delta x, and that's b minus a over n. Okay, so the width of each rectangle is 2 minus 0 over n. So we get 2 over n. Okay, so that's how many intervals we're going to have. Then we start looking at our x values. Okay? And we want an infinite number of them. So we have our first x value. Okay? So when x is 0, the function is 0. When x is 1, okay, the function at 1 is 1, or we would just say 1 times delta x. Our second x value is 2 times delta x. Our third x value would be 3 delta x. Then our nth, or n minus 1, is n minus 1 times delta x. Okay, it's just saying we're just breaking it into these subintervals, okay, or our values there. All right, but then we're going to start looking at the sum of these values, okay, because the sum becomes our limit that we're taking up. All right, so the lower sum is defined as delta x times the function at our least values. So our first, second, third, fourth, and so on. All the way up to, because it's lower, it has to be n minus 1. So you're not going all the way up to n, okay? So then it would be using our x values. We have delta x times 0 squared plus delta x squared, because these are our x values, right? Not our function at those. So these are the x values, and then we plug these in for x into our original function. So we're squaring all of these, okay? Then it would be plus 2 times delta x squared plus x minus, or n minus 1 times delta x squared. Okay, so simplifying even more, okay, we get delta x on the outside. 0 squared is 0. Then we get delta x squared plus, this would be 4 times delta x squared plus, didn't put it here, 3 delta x would be 9 delta x squared plus n minus 1 squared times delta x squared. Okay, so we're trying to simplify this to be able to take a limit. So then they all have a delta x, so we're going to factor out another delta x squared, and then it's 1 plus 4 plus 9 plus n minus 1 squared. I miss my big whiteboards. Okay. All right. So it's on your notes, but that's where we're at. Okay. Right here, we're just trying to simplify this sum. Okay. Then I'm going to simplify it again. And we end up with the lower sum is equal to delta x cubed, because we had delta x times delta x squared, times 1 plus 4 plus 9 plus n minus 1 squared. Okay, then plugging in, we know that delta x was 2 over n, because that's the width of our bar. So it's 2 over n cubed times, okay, if we were to write this all out, you're going to get n minus 1 times n minus 1 plus 1 plus 2 times n minus 1 plus 1 all over 6. That's something you might need to go back to review, is what this is actually meaning, okay? And then we end up with 4 times n minus 1 times 2n minus 1 over 3n cubed. Okay, just simplifying completely. So that's our lower sum, okay? So then to find the area, it's the limit as n approaches infinity of the lower sum, okay? So this is the limit as n approaches infinity of 4 times n minus 1 times 2n minus 1 over 3n cubed. Actually, it's n squared, sorry, because this term is n, so they end up canceling. Okay, so evaluating a limit, we can pull out the constant, so it's 4/3 times the limit as n approaches infinity. Multiplying this out, we get 2n squared minus 3n plus 1 over 3n squared, or over 3. Over n squared, we pulled out the 3. Okay? All right, then what we know about limits, these are the same. So really what you're looking at is 2n squared over n squared, okay? So as n gets big, that just comes down to the limit being 2. So we get 4/3 times 2. So the area under our curve between 0 and 2 is 8/3. You're still using that lower or that upper sum, but you're having to rewrite it to be an infinite number of rectangles. Instead of being a definite number, okay, you have to use n, as we don't know how many intervals there are. There's an infinite number of them. So that gives us our area under our curve as an exact value.